So we kind of talked through, I'll put this whole slide up here so we can see the question. Okay. We talked through this idea that sometimes a reaction like this that produces a gas, you might want to go ahead and collect it in a bottle that's over water. Okay, and then you have kind of introduce a new sort of term. So here's my bottle. Here's my inverted bottle. Okay, here's my water outside the bottle. Here's my water inside the bottle. Okay, and the way this works is basically this gas is being collected right there. So remember we saw before it's like a tube. You know, they have like a tube that goes, your O2 is going up in that tube. So up here, we actually, of course, we have O2, but we also have, just kind of reminding you what we talked about, we have a pressure that's exerted by the O2, but we also, because it's collected over water, have a pressure exerted by the water vapor. Okay? And because the level is equal inside as to outside, actually that total pressure in that chamber that's trapped there is equal to the barometric pressure. Whatever the weatherman, I think that's so funny, whatever the weatherman tells you the barometric pressure is. Okay? Cool. And then remember that we said that actually, I'll go ahead and circle this partial pressure of water. Remember that's like a saturated that's a saturated vapor pressure of water at a particular temperature. So actually to work this problem, kind of working ahead, they give us the temperature that it's hanging out at. To know what the partial pressure of water is, all we got to do is if you go back a few slides, find 25 degrees Celsius, whatever that equilibrium vapor pressure of water is, that's what the partial pressure of water is in that container. So that's kind of setting up what we're doing. All right, so they go ahead and what else did they tell us? Well, they don't give us the mass of the KClO3, but they do give us the volume. So the volume that's containing both of those gases is 0.250 liters. And they give us the total gas pressure. Now that would be equal to the barometric pressure. That's P sub BAR. Okay. It gives the temperature. T is equal to 25 degrees Celsius. Remember, if I circle it, that means you've got to fix it to Kelvin. So what is the mass of the O2 collected? So we know that there is the relationship between pressure, volume, number of moles, and temperature. Do you see where we have, well, first off, do you see where, since we have this, okay, the barometric pressure, I said, is 764 millimeters mercury. We would get the partial pressure of O2 from the table. Do you see where we can go ahead and get this one right here? We can calculate that right now if we wanted to. The partial pressure of O2. So we have pressure, we have volume, we don't have N, but do we have temperature? Yes. So actually we can knock out number of moles of O2 right now. And then we can go from moles of O2 to grams of O2. And then the second question is how are we going to get the mass of the reactant? Well, we're going to use stoichiometry to basically go from moles of O2 back to moles of KClO3. So that's kind of the crux of what we're going to do here. So they gave us the total pressure, the partial pressure of water vapor at that temperature. If you look it up on the table a few slides ago, at 25 Celsius, you're looking at 24 millimeters of mercury. Cool. So we go ahead and subtract. So we take the barometric pressure, or the total pressure, 764 millimeters of mercury. From that, we subtract 24 millimeters of mercury. Round according to the ones place, we get 740 millimeters of mercury. So that's our partial pressure of O2. You guys have complete slides. I forgot about that. Okay. So we rearrange P equals nRT, solving for N. Very carefully rearrange it. Okay. So then we plug in. We're going to plug in. But remember we had to fix the temperature by adding 273. That gives us 298 Kelvin. So now we also had to fix the millimeters of mercury. So we know that there's exactly 760 millimeters of mercury in 1 atmosphere. So we're looking at 0.974 atmospheres as our partial pressure of O2. Now we can plug in. So the number of moles is equal to the pressure times the volume divided by the ideal gas law constant times the temperature. Notice units of atmospheres and liters and Kelvin cancel. That leaves us units with 1 over moles in the denominator, which is the same thing as moles in the numerator. So we're allowed 3 significant figures, 0.00998 moles of O2, and we're almost ready to answer this first question. So to get from moles to grams, we just have to use the molar mass of O2, which is 32.00, right? So that translates to 0.319 grams of O2. Then to answer the last question, this is kind of what we see in chemistry sometimes. We just revisit those moles of O2 we had before, use stoichiometry, okay, to get to moles of KClO3. Then we need to use the molar mass of KClO3. So the molar mass of KClO3, remember your final exam is going to have those problems at the end where you have to show your work. This has multiple choice, then it has problems to show your work. Remember that you have to show something like this, coming up with the molar mass. So we plug that in where appropriate. So we had 0.00995 is our N for moles of O2. From the balanced chemical equation, we know that 2 moles of KClO3 will produce 3 moles of O2. Moles of O2 cancel. Then we throw in the molar mass. We want to use the non-flipped version so that we're left with grams of KClO3, moles of KClO3 cancel. And so it looks like we need to round according to 3 significant figures. And voila, 0.813 grams of KClO3. So these will be for extra credit when you come to take your test on Friday. So as usual, I've got one of these out here, just itching to be seen. So the first problem looks like this, where we have, and you should start getting in the habit of looking at what the physical phases of everything is. So we have the mass of aluminum is given. It's a solid. It's a limited reactant, so we can do stoichiometry based upon the aluminum. The only product that we have as a gas is H2, and actually that's what we're after. Oops, sorry. Come back here. Maybe. All right. So notice they give the barometric pressure, which again is the combination of the H2O, equilibrium vapor pressure we can get from the table, and the partial pressure of H2, which is actually what we're going to need to plug into our ideal gas law equation to get something. So once we get the partial pressure of hydrogen from this relationship, we know the number of moles from stoichiometry, because remember they gave us the aluminum. And of course we need to clear up the 25 degrees Celsius to get the units of Kelvin. Then we'll know everything except for volume, and that's what we're trying to find. And that'll be it. The next one, again, we don't necessarily have a chemical reaction going on, but they said that oxygen is trapped this way. So actually it's, it's wet, okay? And they give the barometric pressure. We can then find the partial pressure of oxygen. Actually, that's A, so that's pretty easy. A is pretty easy. Now B, I was glad to look back in my notes and remind me how this works, because I don't think I said it anywhere in lecture. But when they ask for the volume percent relative to the O2 and the H2O gaseous, that's the same thing as the pressure percent. So what that looks like is just the partial pressure of oxygen over the total pressure, which is the barometric pressure. For C, it just says, for C, how many grams of O2 are present? Well, if you can come up with a number of moles, you're just a molar mass away from getting to grams of O2. So by this time, you know partial pressure of oxygen, you know the volume that those two gases are running around in, of course you know R and T. So it's kind of like a regular one after that. All right. So, on to non-ideally. All right. So the ideal gas law equation must only work for ideal gases. So, and it's true. Actually, we're going to doctor the ideal gas law equation up just a little bit for working with gases that are not behaving ideally. But, so just to kind of remind you, I have this slide coming up again. You guys don't have this slide. This is back in part 1. What is an ideal gas? Well, we said that a gas is behaving ideally if basically they don't care that each other gas particles are there. There's no intermolecular bonds. And the other one is basically their volume is 0, which is kind of weird. That sounds almost like an Einstein thing, okay? But the volume is negligible relative to the volume of the container they're bouncing around in, okay? Then it's behaving ideally. So in general, I'll go ahead and clear back in Chem 1. Here's our little boxes. This is going to be my solid. This is going to be my liquid. This is going to be my gas. And these particles, solid particles, have the least amount of kinetic energy. They're very tight. Okay. Liquid particles have more kinetic energy, some intermolecular bonds, but fewer intermolecular bonds. And gas particles are like this. They have a lot of kinetic energy, basically no intermolecular bonds. So that's why this kind of talks about ideal behavior and its material in its liquid phase. The closer the gas is to becoming a liquid, so the closer the gas is to becoming a liquid, the more it's what we say non-ideal. And does that not make sense with regard to the 2 criteria I just told you? I said a gas is going to be ideal if basically there is no intermolecular bonds, and that's not the case with a liquid. A gas will behave ideally if basically its volume is negligible relative to the container it's being contained in, and that's not the case with liquids either. Okay, and that has to do with basically kind of a density issue is what I think of it. The other one, the other statement says it will be behaving more ideally the farther the gas is from being a liquid. Okay, so that's just about what we mean. Now, before I go on to the next slide here, you guys would probably tell me that if I heat up a gas, or I should say at higher temperatures, heat up a liquid, I can vaporize it. Okay, you take a liquid, heat it up, you can get a gas. Have you guys ever seen, or not ever seen, but I know I've talked about liquid air, liquid nitrogen. You're like, really? Because air and nitrogen's a gas. But what they do is they cool it down, but the other thing is they pressurize the darn thing. Okay? So I'm going to do this. Go this way. If we pressurize it, if you pressurize a gas, by golly, you're going to make those intermolecular bonds form whether they want to or not. And you can go ahead and make a gas into a liquid. Happens all the time. Solid dry ice is basically all the way over here. Carbon dioxide, it's pressurized, cooled down to the point where basically now it's not a gas, it's a solid. Okay. Okay. So in general chemistry too, one of the next things we're going to talk about down the road will be physical phases and physical phase diagrams. And so actually this is your first look at a physical phase diagram. So the way you look at this is there are, I don't know if you can see them, but there are actually 3 sectors. Okay, a sector for solid, a sector for liquid, and a sector for gas. There are phase diagrams, but sometimes they're called pressure temperature phase diagrams. So along the y-axis is pressure, and along the x-axis is temperature. So the sectors look like this, where the sector clear over here, and if you look at the x-axis, I mean, this is cold, right? We have basically a sector over here that's solid. We have a sector kind of in the middle of the Y that's a liquid. Then we have a sector over here that's a gas. Actually, there's a third sector called supercritical fluids, but we'll talk about that later. So these 3 physical phases of matter, they make sense, right? Something's warm, it's a gas. Okay, something's cold, it's a solid. Something in between, it's a liquid. But actually, pressure is a player too. So this is to say that for instance, at 25 degrees Celsius, it's kind of room temperature here, okay? And at 1 atmosphere, let's see, pressures and atmospheres are down here. Okay. This particular, I think this is for CO2, it's a gas. This is so cool, though. I just think this is awesome. So, but what's to say if we go down to, oh my gosh, like a negative 50, okay? Negative 50 at maybe 1 atmosphere, it's also a gas. But negative 50 at 2 atmospheres, I'm solid. Okay? Is that not cool or what? Right here, this back and forth, this is actually the place between the gas and the solids. But my point here with regard to gases behaving ideally is that it will behave more ideally when it's farther away from a liquid. So we decided that's higher temperatures and lower pressures. So on this phase diagram, you're kind of looking at higher temperatures and lower pressures. It'll be less ideal if it's at lower temperatures and higher pressures. So that would kind of take us up to that corner. All right. So this is what I showed you just a minute ago. So with regard to gas particles having intermolecular bonds, the lower the temperature is, it's kind of funny. It's like which came first, the chicken or the egg? But I think they slow down, okay, and they're more likely to grab a hold of each other. Or was it they let go of each other and then they're more likely to run around with higher kinetic energy? I don't know. Okay. Then with regard to the gas particle having basically negligible volume relative to the container it's running around in, if you're at high pressures, okay, basically you have made your gas pretty darn dense, and it's not going to behave ideally because its volume is significant relative to the container you've confined it to. So it's less likely to be true at high temperatures. Okay, so I said that actually there's a way to fix up PV equals nRT, and here's how you fix it up for non-ideal behavior. It's called van der Waals equation of state. So see if you can recognize PV equals nRT here. That's our P term. That's our V term. PV is equal to nRT. Okay? So the thing that's different, the N is the normal, the V is normal, okay? The R and the T and the P are normal. What's not normal is the A and the B. So actually those are constants for a particular gas. On the next slide I have, of course you never would have to memorize this, but I have a gas and then I have van der Waals constant A and B. And you would plug it into here. Oops. Van der Waals constants. So PV is equal to nRT. So the A quantity, N over V raised to the second power, that actually corrects the pressure, okay? And that's accounting for intermolecular forces. So I was playing around with this in my office. So can you see where we do this a lot with equations in physical science? So if this term basically goes to 0, then the gas is behaving ideally. That makes sense? I think so. And how are you going to get a 0 term out of that? Well, you could do a few things. You could make N really small number of particles, small number of moles, or you could make V very large. And it's just what we've been talking about. Makes sense. So the Bn corrects for volume. Again, if our goal is to basically go back to our normal volume, then we want that to basically go to 0. And how are you going to get that to go to 0? Make N, the number of moles, very small, relatively small. Makes sense. So I don't even do an example for you. But here are an assortment of gases and their van der Waals constants, just in case you ever need them. And I couldn't tell you necessarily, it must be experimentation that they came up with these, but you can see where the larger the correction factor, the less ideal behavior. So, okay?
Are you going to have one of these monstrous equations on the final?
No.
Aww.
No, you won't have it on, you won't have it on the final, but I guess it would be fair game for a multiple choice question.
Okay.
You know, I mean, how do you correct for, you know, non-ideal behavior? The answer is Van der Waals
Van der Waals
equation.
equation.
Yep. You don't have a problem to work out, but there's a lot of things in chemistry that not necessarily a problem, but a concept to kind of know. Okay? And that's all I got. See you tomorrow.
Yes.
Yeah.
Final class.